Okay, another thing. So we have gone through this various factors affecting plants, and I bet some students started feeling like overwhelmed because so much. As I said on the week one, it's going to be overwhelming amount of information. But today is basically the end of individual factors, and then next week we will be learning energy balance, which is a little bit challenging content too. So don't get intimidated, but it's very important content because we need to understand, energy balance of the leaf, and that's the content. And then after that, we expand our knowledge into the canopy. So the canopy is the group of plants growing together. So we exercise, the understanding up to today in the canopy. So I think you have opportunity. That's my intention, to enrich your understanding by switching the target from just single leaf or just one plant to the community. So if you feel a little bit overwhelmed, let me know. We can talk about that, and then I can probably help what is not so important and what is important. And that's probably helpful. Yeah. Okay. Okie dokie. So the temperature was interesting, right? Temperature, if you remember Monday lecture. Okay. DIF, DIF. What's the DIF abbreviation? DIF coming from DIF? Yeah. The DIF is the difference between daytime temperature and nighttime temperature, and DIF is coming from the 3 letters of DIF, difference. And how was DIF used? Anyone? TJ? Control elongation, yeah. Typically for floriculture, bedding plants, pot plants production. And then I gave the Easter lily example. And then many more other species are known to respond to DIF, but not all species, responding to DIF. So depending on the species. TJ?
My question was, so the DIF is, the temperatures we're taking into account the average for 24-hour period?
Yeah.
So the DIF goes into that, right?
Right.
So how long does that temperature difference have to be in existence? Because you can drive the temperature down at the end of the day, and then you're heating the greenhouse for the night. Or you could do the same thing.
Yeah. So TJ's question, basically, instead of average of over the whole period of night and day, is individual temperature period, like a beginning of the night or end of the night, more effective to cause the stem elongation? It's a great question, and then I think there was a study, and I need to look up, but the growers were doing early day temperature drop instead of doing a large negative DIF, because that is easier, and that's what I remember. But yeah, so there is a sensitive temperature. Yeah, I think so. Yeah, I need to look up to make sure that my answer is correct. But that's what I remember. Early morning, instead of doing entire day low temperature and entire night high temperature to create negative diff, they do temperature drop. Early in the morning, huge drop, and then let it warm up. But anyway, I need to confirm that. Good question. Yes?
Based on what we talked about last time, nighttime temperature should be higher?
If you want to reduce the stem elongation rate, yeah. If you want to if you have a capacity to do that, that meaning you need to lower the daytime temperature, right? Yeah. So then yeah, nighttime temperature is greater than daytime. Then you get very, very compact, short plants at the end.
Day versus night, or I'm sorry, day minus night.
Yeah, it's always day minus night. So that's why there is a negative value, there is positive value. Okay, it's not just absolute value. Yes?
The negative be shorter and the positive be longer?
Positive is longer and negative is more negative. Yeah, yeah. So, but within the positive values, small positive should give shorter plants than large positive, because it's linear response over the diff, right? So, okay, all right. It's quite interesting, and then it has been used in industry. Okay, so it's not just the scientific exercise; it's actually utilized technique. So that's why TJ has a computer control system in his greenhouse, and then it has a function of diff, right, to compute the diff. So it's been used. All right, good. Okay, so now we are going to talk about water vapor. All right, water vapor, water vapor. Here you go. This is also a little bit engineering. So how many of you are actually engineers? Engineers? 1, 2, 3, 4? Okay, okay. So most of them plant science. So engineers probably familiar with this content, because you guys learn what mixing air and thermodynamics and all that. Plant scientists don't usually, but greenhouse physiology, if you have this understanding, really helpful. So that's why I put this as one of the topic. Humidity, it's very important. We all live in desert, so you know that. It's very important. It affects plants, affects human beings and everything. So plant response to water vapor, and then there is one reading material in a D2L that is actually post-harvest technology textbook, one chapter. So it's a lot of psychrometrics I talk about today is written in a way plant scientists or horticulturists can understand. So that's why I picked that, because it's a good summary of humidity environment. Okay, so terminology, you guys probably already familiar with evaporation, transpiration, evapotranspiration. Is evapotranspiration new word for you? Or you have heard of that? You have, yeah. So the evaporation is just the change of state from liquid to gas, and transpiration is the evaporation from plant tissue, right? So that's transpiration. So we kind of separate out evaporation and transpiration. But whenever we need to estimate the total moisture, coming out from the system, and that contains evaporation and also transpiration, we call that evapotranspiration together. Okay? Some of the moisture is from the soil, some of the moisture coming from the plants. In that case, evapotranspiration. Right? Okay. So transpiration we looked at as a diffusion. When we talked about CO2 diffusion, we also did the water vapor diffusion from the stomatal cavity to the air, outside the stomata, the same way, as a diffusion. So stomatal cavity usually saturated because it's such a tiny space surrounded by wet, cells. Therefore, it's usually saturated at that temperature. Okay, so the saturated moisture coming out to the non-saturated air. Okay, all right, easy, right? Easy. So that difference in terms of moisture concentration in the, which is saturated, but the actual concentration, how much grams of moisture in the volume of air, or we sometimes use, we often use the vapor pressure instead of grams per cubic meter vapor concentration. I guess that's a practice to express the gas concentration, but CO2 is usually volumetric percentage or micromoles per mole, but somehow water vapor, even it is the same gas, we use partial pressure. Okay, whatever the reason. But it's a ratio. You can convert, partial pressure Pascal into the volumetric concentration or mass per volume concentration if we want to. But anyway, so it's saturating here, and then non-saturating here, and then the difference is the driving force of the transpiration rate, as long as, the stomata are open. If stomata is closed, then even though you have a huge driving force, transpiration wouldn't happen because it's closed, right? All right, or a very minimum, because from the surface, cuticular surface, you can get some transpiration going on. All right, so the minimum transpiration when stomata are completely closed. Okay, so plant response to water vapor. So that when stomata are open, and that means the same stomatal conductance, transpiration is usually affected by humidity. In the air, okay, in the air. And when humidity is high, then sorry, the other way. When humidity is low, then transpiration increase. When stomata are open. When stomata are closed, that's it doesn't affect. But when stomata are open, declining humidity actually causing increasing transpiration rate because it's a driving force between the cavity and then also air. And transpiration rate is also affected bunch of different factors. And then this part you can probably better understand when we talk about energy balance, because the conditions are all related with the energy balance of the leaf, such as leaf temperature or light and air current speed, things like that. Okay, and we really want to understand moisture in the air, and then also how it affects the plant, because it's very important in crop production, crop physiology under controlled environment. And the good thing is you can control the humidity level. All right, so what is humidity is the question. What is humidity? How do you quantify your humidity? So what is today's humidity? Can anyone answer? About 20%. 20%, okay. So what is percent against?
Relative to the maximum that it can hold at a certain temperature?
Yeah. So there's one answer relative to the air volume, another answer relative to the saturation at that temperature. Yeah, saturation, how much maximum amount the air can hold. Right. The answer is you are right. So that's percentage relative to the maximum, and then the maximum changes at different temperatures. If you increase the temperature, the amount of saturation increases. Okay, all right. So going back to the plant response, before going further, humidity affects stomatal closure, and particularly we know that low humidity close the stomata. And once that happens, not just transpiration, but other gas exchange, in our case photosynthesis, net photosynthetic rate, is also affected. Therefore, humidity indirectly affecting net photosynthetic rate, because humidity affects the stomatal opening, therefore photosynthesis is also affected. So that's why if you grow plants in too low humidity condition, plants don't grow really well compared to the conditions optimum to the plants. There is the range of humidity plants can function better than the other conditions or the other level of humidity. And then also the third one is, you probably understand better next week, but humidity does affect temperature of the plant also. Easier way to understand this is because humidity affects the transpiration, and transpiration is the cooling process. Therefore, it does affect temperature. humidity affects the temperature of the leaf.
How does humidity make temperature increase? If there's
When humidity is high, right, and then transpiration is reduced, then temperature goes up. Yeah, you would have a complete understanding of that dynamics next week. All right, look forward to that. Plants are very sensitive to humidity, and this one is the net photosynthetic rate responding to humidity. And again, this is through the stomatal closing. Okay, so the humidity is declining from left-hand side to right-hand side in x-axis. So the high humidity to your left, low humidity to your right, and then this is the net photosynthetic rate of raspberry plants under controlled environment. And then they are measuring net photosynthetic rate as a gas exchange, so how much CO2 is taken up. And then you can see that decline of net photosynthetic rate as you decline the humidity. All right? And then when temperature is higher, the reduction of photosynthesis is much faster than when temperature is cooler or lower. All right? So, so that is the sort of evidence plant responds to humidity, in this case more a short period of time, net photosynthetic rate. So back to the definition of relative humidity, that's a percent water vapor pressure or the concentration of moisture in the air over the saturated water vapor pressure, so the saturation concentration of water vapor at the same temperature. So the percent ratio of those two. So when you say today's humidity is 20%, that means 80% more to get saturated. Okay, make sense? All right. So you have series of new terminologies from here. Before going that, so when we say humidity, that means usually relative humidity. Okay, but we don't usually say relative humidity in your conversation, but it is actually relative humidity. And then there is actually absolute humidity, and that's the new terminology for most of you. And absolute humidity is the absolute mass, the mass of the water vapor in the air expressed per cubic meter of volume of air. And this value is useful when you need to compute how much grams of water is going to be condensed or how much grams of water needs to be evaporated to reach certain percent humidity. To do that kind of computation, expressing humidity using absolute humidity is much easier to do so than expressing humidity using relative humidity. Okay? All right. So, any question? Right. So vapor pressure, water vapor concentration in moist air expressed as partial pressure. So I already mentioned that. The unit is scientific writing, and then also nowadays, particularly European or Asian controller, we use Pascal for the vapor pressure concentration. Okay? All right. So, one more, actually two more, in terms of terminology. So those terminologies very important. The first two is important to understand psychrometric. We are doing exercise today. Dry bulb temperature and wet bulb temperature. So dry bulb temperature is basically the temperature, air temperature you are measuring, but the sensor is always dry, right? So that's why we call dry bulb temperature. To separate from the wet bulb temperature. So wet bulb temperature sensor is always wet. Sensing point is wet with water, pure water. And sensing the equilibrium wet surface temperature. Okay? So in a non-saturated humidity environment, like here, maybe, I don't know, 20%, let's say 20%. I have two sensors. Imagine I have two sensors. One is dry bulb temperature sensor, so it's just dry. And the other one is wet bulb temperature. It's wet. all right? So dry and wet. Which temperature is lower? Dry bulb temperature or wet bulb temperature? Under 20% humidity. This is an evaporating surface, wet bulb. Wet bulb is colder, yeah. Wet bulb is colder. Okay, so you are in the summer or maybe in the fall or spring. Whenever the temperature is right, you jump into your pool, for example, right? Come out and super cold. Have you experienced that? And you need to wrap up with your, beach towel. Otherwise, you get freezing because the wet bulb temperature, even though outside is 40 degrees or 110, whatever, high temperature, wet bulb temperature could be as low as 12 degrees C, which is 55 here. All right? So that's why you feel cold. But you do that in Florida, very different, right? You don't get that cold feeling. Why? Because wet bulb temperature is much higher, very close to the dry bulb temperature. So the same question, dry bulb temperature and wet bulb temperature in Florida situation, those two temperatures getting very, very close because of high humidity. It's not evaporating much in here. So the wet bulb temperature is an indicator how much evaporation potentially goes. Okay? And that is measured with temperature. Okay? If it is saturated, what happened? This is 100% humidity saturation situation. Saturated, wet bulb temperature, or the other way. Dry bulb temperature, wet bulb temperature. Same. That's right. No evaporation in a wet bulb. Therefore, temperature is the same. Okay? All right. You did a lot already. Good. Okay. So you understand dry bulb, wet bulb. So then I have a sensors if you want to see wet bulb temperature sensor. It's very primitive, just sensor wrapped with, the cloth, and then we have to soak with the DI water to get, because the salts affect, so we have to use DI water. But anyway, if you are interested to see that, I can show you. We use that for calibrating humidity sensor. Because knowing wet bulb and dry bulb, you can find humidity, relative humidity, absolute humidity. Dew point, that's also very important for both engineers and then also scientists, and then also growers, because dew point is important to understand condensation. So the condensation occurs when the temperature goes below the dew point. Okay? So that this temperature, right now, 24, 25 degrees C, right? And then humidity is 20% right now. If I start cooling this room, the capacity of the air to hold moisture is going to decline. Okay? And then the moisture content eventually exceeds the capacity of the air because of the low temperature. And if that happens, you see the dew condensation. Okay? Yeah? So if you have a cold can of Coke, all right, take out from your refrigerator, right? You are living in desert, so you don't really see condensation much on the surface of the can. But if you go to Florida, again, Florida is an example, you have a massive amount of condensation, right? Like in a restaurant, have a glass water, and then in Arizona, it's just a little bit of sort of wet surface, right? Glass surface. But if you go to somewhere else, then you got massive water, yeah, dripping, basically. And why? Because the surface temperature of the glass is lower than the dew point. And then dew point is determined by the moisture content of the current. So that we see exercise in a psychrometric. But remember, condensation occurs when temperature of that surface attaching the air, temperature of that surface goes below the dew point, okay, not above the dew point. So when you see the greenhouse having a huge condensation in the surface, that means the surface of the greenhouse is lower than the dew point in the greenhouse. Okay, some people misunderstand that that's the 100% humidity situation when you see the condensation in the greenhouse, but it's not. It's just the surface is lower than dew point, therefore there is condensation going on. If you enter that, the greenhouse may be just 60% humidity, maybe 70% humidity, but because the surface, you know, the wall or glazing is lower than the dew point, that's why condensation happens. It's very important to understand. Another example is the produce. You know, you are chilling the produce from the field and then shipping, and then it's a cold chain, so from one location to the other, and some location has a, you know, wrong temperature control, therefore the fruit surface was below the dew point and then start condensating on the surface. And something like that you never understand without understanding dew point. Okay, there's one exercise in the homework for graduate students using this dew point understanding. So take a look. That's also for undergraduate students bonus points. So if you want to do that, you're welcome to do so. But it's really important information. All right, so before going that, so relative humidity, this is the equation. So the current vapor pressure divided by saturation times 100 to get percentage, right? You already understand that. This is a percent to the saturation. And saturation vapor pressure is depending on the temperature and then almost exponentially increasing by increasing air temperature. So the 10 degrees C air and 50 degrees C air, the amount that, you know, the air can hold regarding water vapor is what? More than 10 times. More than 10 times. 10 degrees C and 50 degrees C. And sort of rule of thumb, nearly double saturation for every 11 degrees C. Okay, so about 10 degrees C. Then your air capacity, the capacity of the air to hold, you know, the moisture is going to be doubled. And then this is an equation. You don't need to remember or anything, but it is empirical equation based on the measurements. Okay, so here's a exercise one. 10% humidity, relative humidity at 30 degrees C, and 60% relative humidity 30 degrees C. Okay, the same temperature, but low temperature and high temperature. Which condition you expect evaporation, more evaporation? 10%? 10% humidity? How many of you think 10%? So the evaporation happens when it is dry, right? Okay, so which is drier, 10% or 60%? 10? Yeah, okay, easy, right? Next one, the same humidity, relative humidity, 60%, but different temperature. 10 degrees C, 60%, and 30 degrees C, 60%. So the winter time, 60%, summertime, 60%. Which one you think is drier or feel dry? 30 degrees C. Yeah, yeah. Okay, getting a little bit more complex. 20% humidity at 10 degrees C, 60%, 30 degrees C. Which one is? 60%, 30 degrees C? Okay. It's kind of getting challenging, right? It's not so easy to answer this kind of question. So what do you use in this case? Temperature is changing and humidity is also different. Because humidity, relative humidity is based on the saturation at that temperature. So the base value is changing when temperature changes. So in that case, you need to have different value to compare the capacity of the air to hold moisture. So that's the driving force of the evaporation. So what is the value? So that is VPD. Which way I go? Oh, this way. Yep. So vapor pressure deficit is the VPD. And VPD is the difference between the saturation and actual water vapor pressure. So if I use Elmo, I can clearly show that. Okay. All right. So the relative humidity was the current over the saturation times 100, right? So that's relative humidity. And the issue is saturation changes at different temperatures. But VPD is actually saturation minus the current. So it doesn't affect the like this because it changes, but it just increases the difference. So it's just the pure capacity. It's not the relative capacity, pure capacity of the air to hold more moisture. So the VPD is the difference of the saturated vapor pressure and the current vapor pressure. So meaning how much more the current air can hold, how much more moisture. Okay, the unit is kilopascal. Most of the case, or Pascal, if the value is very small, right? This one is percent. Okay? All right. Okay, and then some people use humidity deficit, particularly a Dutch, I think, computer controller has humidity deficit instead of vapor pressure deficit. That's based on absolute humidity, but saturated absolute humidity minus the current absolute humidity. The meaning is the same, just different unit. Okay, all right. So this is a table format to understand vapor pressure and vapor pressure deficit. So this is a 10 degrees C, and this is a high humidity, 100%. So this is a saturation condition, right? 100% is a saturation. And this is the saturation vapor pressure, 1.28 kilopascal. And 60% of air, that means 60% of 1.28 kilopascal. So that's why 1.28 times 0.6 equal 0.74. So the 60% amount of vapor pressure, right? So 60% humidity at 10 degrees C. If I ask what is the vapor pressure deficit, how you compute that? So you take the saturation under the same temperature, and then you find the current vapor pressure, which is 0.74, and the difference, so 1.28 minus 0.74 is 0.54. So saturation minus the current is the vapor pressure deficit, VPD. So you see that as humidity goes down from 100%, 60%, 20%, vapor pressure deficit increase, right? Because the humidity goes down, that means more capacity for the air to hold, right? Saturation, 20 degrees C, the saturation is much larger, but the same trend, when humidity decline, then the VPD increase. So the high VPD meaning low humidity, basically, okay? So it's a little bit counterintuitive, but greater the VPD meaning lower the humidity. Okay. All right, and then again, VPD equals saturation vapor pressure minus current vapor pressure, okay? All right, and then why VPD is so useful? Because if you take the evaporation and VPD in a graph and plot the evaporation rate against the VPD, you see this kind of linear response. So that's why it is easy to understand the capacity or potential evaporation. using BPD. All right. Okay, so the next in this today's lecture, you're gonna understand the psychrometric chart. So the psychrometric chart is something engineers use, and then plant scientists, you probably wouldn't have opportunities unless you're working on evaporation, transpiration in your study. But this helps you to understand the relationship of all the moisture-related parameters and variables. So, but at the end, you have a tool, electric or digital psychrometric chart. So you don't need to actually use the paper base anymore. But understand the structure of the psychrometric really helpful. So use this. Let me explain what it is. So the psychrometric chart basically shows all the the moisture-related values. So as long as you know two values, you can find everything else. Okay, two values, maybe temperature and humidity, or maybe wet bulb temperature and dry bulb temperature. Super easy. So this is a typical structure or shape of the psychrometric chart. The horizontal axis is the dry bulb temperature. So this has 0, 10, 20, and 30. And then vertical axis is the amount of moisture. And I like to see vapor pressure in the y-axis or the vertical axis. But some people use humidity ratio, which is another engineering term you don't need to remember unless you are engineer. But anyway, so any intercept can find the other temperature or the other parameters. For example, all right, so I have, and then another thing. So there is a curves like that, right? There are curves, and that's the humidity line. So this is 100% saturation humidity line, 80%, 60%, 40%, 20%. And you can find the point representing your air's condition, so the temperature, humidity, for example. So I can find 30 degrees C and let's say 40% humidity. So 30 degrees C line is here. So this is a 30 degrees C line because this is 20, this is 10. So this is 30 degrees C line, dry bulb temperature, so the air temperature. And then I can find the intercept or the coordinate of the temperature and humidity. And in my case, it's 40%. So this is my point. Okay, so that's 30 degrees C and 40%. Okay, and then as soon as I know here, I can find wet bulb temperature. Okay, so wet bulb temperature is plot on the diagonal way, in diagonal way like this. 0 degrees C wet bulb temperature, 10, 20, 30. And then I can find, okay, so this is close enough to the 20 degrees C wet bulb temperature line. So therefore, my air of 30 degrees C, 40% relative humidity has wet bulb temperature of 20 degrees C, right? So if I have a surface evaporating surface, then it's likely to have that low temperature, 10 degrees C lower, right? And then I can find vapor pressure, 40%, 30 degrees C, vapor pressure. You can read this vertical axis, and then you see it's about 1.75 unit kilopascal, all right? And then what is the saturation? Saturation vapor pressure at 30 degrees C. The same way, just look at the 100%. This is a 100% line. So the 30 degrees C and 100% right here. So the saturation is a little off the range, but I can guess 4.25 kilopascal as a saturation. So this is my current, and this is a potential saturation, right? Current 30 degrees C, 40%, potential 100% humidity, so the potential saturation vapor pressure. This is a current. So what is the VPD of, the question is 30 degrees C and 40% airs VPD. Saturation minus current. Saturation is 4.25. The current is 1.75. So this is the, 30 degrees C, right? The current, saturation, this, the distance or the value, the difference is the VPD. And the value is what? 0.5, right? Kilopascal. Okay? All right. So let's see, 10 degrees C, right here, 10 degrees C, and 40%, the same relative humidity, 10 degrees C, 40%. You can visually see that the vapor pressure deficit is going to be this, right? Saturation and the current. Visually see that vapor pressure deficit at the same humidity level but different temperature is much smaller than this higher temperature situation, right? The same 40% air, the humidity wise, but different temperature, but see that vapor pressure is very different, okay? So that's why we are not using percent humidity to express the humidity or the dryness of the air. We use VPD to express that, because relative humidity is not corresponding to that capacity. Are you with me? Okay, good. All right. All right. So that's the psychrometric chart. And then this one is I think it's in the homework, all right? And it's a little bit busy. So you can use this or you can use digital version if you don't like to use this. But it used to be we did everything in a psychrometric chart, old-time people. But this one is a slightly different version. So this is the dry bulb temperature. That's the same as the simple version I used as an exercise. The y-axis, instead of having the direct number of vapor pressure, it has a humidity ratio, so different value, but it shows the conversion factor. Here, to get the kilopascal vapor pressure in kilopascal, it says multiplied by 151.9. So whatever you read in this chart, you need to, for example, 0.014 in this tiny little font times 151.9, you get kilopascal reading of vapor pressure. So it's just a little, process you need to do that. But anyway, the same way, curves are percent humidity, relative humidity, and diagonal lines are wet bulb temperature. So again, as long as you know two values, you can find either humidity or vapor pressure or VPD. I'm in a greenhouse. So for you guys, this is a much easier version, digital site chart. So this is, you can download. It's a free software. It's developed by Taiwanese engineer. And you can go this link, and I have a link already in the D2L, and then save in your computer. I don't think this works on Macintosh though, so you need to have a Macintosh emulator to run the Windows, or whatever you call. I forgot what it is. But anyway, so it has to be on Windows. So, but it should work. So I have in here. All right, the same. Okay, so basically, this is the air temperature, and this is the relative humidity, and wet bulb temperature, dry bulb, no. This is the dew point temperature, DP. TDP is the dew point. And then some other, here, this is saturated vapor pressure. Yeah, so the message tells you what it is. And this is the current vapor pressure. Okay, so the current vapor pressure, saturation, and maybe you want to know the dew point and wet bulb and relative humidity. Okay, so if you type any number, for example, 30 degrees C and 40%, so it gives all the other numbers. Okay, very convenient. So you can find the BPD from those two numbers, 4.24 minus 1.6 or 7, then the difference is the BPD. There is a BPD column in here, but this is a different, I'm explaining the terminology confusion, but this guy is also confused by some of the groups using BPD in different meaning. So this doesn't compute what we want. So use this saturation and the current. So those two cells to get the BPD, right? Super easy. I always wish, someone needs to, I always wish someone would develop an application in a cell phone so that I can type in and then just BPD comes up. That would be nice. That would be nice. If you are in a business, you work on that. Okay, great. I can pay $2 for that. Yeah. It doesn't have to be free. All right. Okay, so that's the side chart. What else I have? Okay. All right. Okay, so I want to do terminology. Clarification first. Where is that? Here. Okay, so I just mentioned the BPD issue in the psychrometric chart, side chart, the digital version, because people use BPD in different ways, and it's not really settled yet. But I stick with what ecophysiologists and ecophysiologists use, and greenhouse engineers and greenhouse scientists use. Some horticulturists mean different value, so that's why this slide is helping you just to clarify, because in the future you may get confused by the two different BPDs. So the vapor pressure deficit, this is widely accepted terminology in controlled environment agriculture and ecophysiology for the difference between saturated vapor pressure and vapor pressure in the air. Okay, that's what exactly you understood today. However, some horticulturists refer to the difference between saturation vapor pressure in the stomatal cavity. So here plants, the concept of plants come in. Not in the air, but in the stomatal cavity, and vapor pressure in the air. And I think some of them are still teaching and using this terminology instead of more widely used BPD. But so you want to make sure when you are communicating or writing paper, which one you want to use or which one the other one is using. The reason they include the stomatal cavity in the VPD concept is because that's the direct factor driving transpiration rate. If you look at here, so this is the vapor pressure saturation of the other VPD's definition includes. And so that leaf temperature based saturation, so that's what they want to use. But the challenge is that leaf temperature could be different at different locations, different conditions. It is very difficult to find the representative leaf temperature. That's why practically it's very difficult to find the value of VPD in growing conditions. That's why it's not being used. It's been taught, but it's not being used because it's not practical. So anyway, the difference is our BPD is the difference between the saturation vapor pressure of the air and at that temperature and the current vapor pressure in the air. And then the other one is the leaf saturation and the air vapor pressure of the air adjacent to the stomata. But anyway, so because of the confusion, ecophysiologists came up with another a little bit confusing terminology. They call vapor pressure difference, and that is basically meaning the difference between leaf saturated vapor pressure minus the current. So instead of just calling BPD, they want to call vapor pressure difference. And when you say vapor pressure deficit, ecophysiologists mean that this is in the air, just like you learned. But because it's very too close in terms of terminology, I usually say leaf to air vapor pressure difference when I want to, consider the saturation based on the leaf temperature. Okay, so when I say leaf to air, that means leaf temperature base. So if you consider the leaf temperature, because remember that in the temperature section, leaf temperature could be a few degrees or several degrees higher or lower, right? So that's why they want to include the leaf temperature in this BPD concept. And then if you can actually do that, then your transpiration rate is pretty much following that the saturated vapor pressure in the stomatal cavity and air vapor pressure difference. So that's leaf air vapor pressure difference. So this is a leaf to air vapor pressure difference, and then we are not going to call this as a BPD, but some people do. So you just make sure what is the terminology whenever you communicate with other groups, okay? All right. Okay, this one is just showing you the range of BPD relative to temperature and percent humidity, relative humidity. I know it's an awful table because it's so small fonts, and you can't even see in your handout, but it's two slide version, probably it's better to see. But the orientation of the table is, this is the humidity level. It's not percent. For some reason, it's not percent. But if you multiply by 100, you get percent humidity. 0 all the way to 99%. So that's humidity columns. And then rows are temperatures from 5 degrees C and 36 degrees C. Okay? And then the color is showing different BPD. So, and then in the range of 0.3 to 1.3 kilopascal. So if you take one low, the value is declining. 10 degrees C, 0% humidity, 1.22 kilopascal, all the way to 0.0 some kilopascal. So it's showing BPD in this table at different combinations of temperature and humidity. And then the color is showing the range of BPDs falling in 0.3 to 1.3. And what is this range? This is the range we often recommend to have in the greenhouse, so that the optimum BPD to grow plants. So you can now, that's why I put this in here, visually see that BPD range, optimum BPD range to grow plants are very different at different temperature, right? At higher temperature, you have to keep the humidity much higher than lower temperature. And then also the window you can achieve the BPD in that range is very, very narrow compared to low temperature range. So that's why under high temperature it is very challenging to grow plants, because the BPD is huge, or tend to get huge, right? And getting the stress, water stress. Because big driving force, BPD equals to evaporation driving force. And if there is a big driving force, then plants tend to lose water quickly and then close stomata. So that's why it is challenging to grow. All right? Okay, and this is conversion from BPD and humidity deficit. It's just for your information type of slide, because you might see different units. So I just computed all the coefficient to convert from BPD to humidity deficit, which is the absolute humidity-based difference between saturation and current. Meaning is the same, but the unit is different. And if you are using greenhouse computer control, some people use humidity deficit. That's why I put this in. And now this figure looks more meaningful because this is a kilopascal saturation vapor pressure deficit. So this is BPD. And this is, again, raspberry plant net photosynthetic rate going down at around 0.5 kilopascal, so which is quite nice BPD for growing tomato and other crop, but this particular crop seems to be very sensitive to vapor pressure deficit. So the greater the vapor pressure deficit is, drier the air is, right? So that's why net photosynthetic rate is declining, because plants try to keep the moisture by closing stomata. Okay, right. And then we done this next week.